All right, type of electromagnetic radiation is wavelength 5.5 times 10 to the negative 7 meters. What's its frequency? How much energy does it have? And I'll throw in another question. What type of radiation is this? So, how are we going to convert out of this meters into we need frequency, and then we need energy. So, what are we going to do first? Do you remember what the equation is, or what the conversion
It's
is?
the speed of light is equal to wavelength multiplied by frequency, and
Okay,
then
and just as long as we know that we're talking about the speed of light, and you know that the speed of light is c, which is, we'll just put 3 times 10 to the 8 meters per second. What are we looking for in this first portion of the question?
um, the wavelength,
No, we were
or
given the wavelength.
we're looking for the frequency then.
Okay, so what are the units for frequency?
Hertz.
One over.
Hertz or 1 over seconds. So I'm just going to start with 3 times 10 to the 8 meters per second because that puts my seconds in the denominator right where I want them.
Are you screen recording right, or are you screen sharing right now?
Yes.
Now you are. There we go.
All right, so I've got the seconds unit in the denominator, which is where I needed to answer this question. And so all I need to do is cancel out the meters.
Mm-hmm.
Sorry, somebody's saying something. Paula is here. There we go. Everybody's here that should be here so far. All right. So I need to get rid of that meters unit and keep the seconds unit, but I was given a meter unit, so I'll just go ahead and use that. So I'm going to need to put 5.5 times 10 to the negative 7th meters in the denominator. And when I do that, then I can cancel the meter unit out. And I'm going to erase this because that line was just too long. Equals. And so now I've got an answer with seconds in the denominator, which is the answer that I'm looking for. So what do we get here? 3 E8 divided by 5.5 E negative 7. Nice big 5.5 times 10 to the 14th. Okay, so that's good. There's our frequency. And then we want to go to energy. So to go to energy, we're going to need to use Planck's constant. And so to use Planck's constant, we use H is equal to 6.626 times 10 to the negative 34th joules times seconds. Okay. So I want to make sure that we approach this second question correctly. So what do you want to do?
We want to cancel out the seconds because we're looking for energy.
Okay, so we just need joules and we want to cancel out seconds. So there's two approaches. What are the two methods we could do this with?
Could we just joules 10 seconds? Could we just put 5.5 times 10 to the 14th in the denominator? And then it would cancel out seconds.
So divide by the frequency.
Yeah.
It's actually multiplied by the frequency because the seconds is already in the denominator.
Yeah.
But no, we're not going to do that. Someone want to tell me why? How'd you like that first multiple choice exam this quarter?
Yeah. So
why did you not like that first multiple choice exam? Give me a couple of reasons. Give me at least one reason.
Sig figs.
Sig figs, giving you answers that were super close together, and you're like, which one of these is right? So the issue with this is that's what's going to happen with this question. So you can answer this question without using the frequency, and I'm not going to use the frequency that we calculated because it's a calculated value. And I can get the answer to this question without using a value that I calculated. Does that make sense?
Yeah.
So if you are taking a standardized test and there's like a series of questions that are all related to each other, if you can answer any one of those questions without using information from a prior question you answered, do that. Because I guarantee you, if you answer this question right here and you use the frequency, I'm going to make sure that the first answer you see is the one you get when the actual answer is going to be like a decimal place different because of rounding error. So we're going to use wavelength. So we need joules, as my answer. So I'm just going to go ahead and start with 6.626 times 10 to the negative 34th joules times seconds. I'm doing that because the joules is in the numerator and I want it there. So now I just need to get rid of the seconds. Okay, so great. I have something that has seconds in it, and that something is 3 times 10 to the 8th meters per second. Okay, cool. So that seconds got canceled out. The problem with this is this constant came with another unit, and it was meters. But that's not a problem because in the question, I had 5.5 times 10 to the negative 7th meters. So then I can cancel those meters out, and the only unit remaining is joules. And so we get 6.626 e negative 34 times 3 e8 divided by 5.5 e negative 7. So we get 3.6 times 10 to the negative 19th joules. And I can't remember, what does it work out to be if I do it the other way?
Oh, if we do the constant divided by our calculation. 626 e negative 34 multiplied by 3.6 e. Is that negative 19?
No, it's not 3.6. We're using the answer we got from the prior question, which was 5.5 times 10 to the 14th.
Oh, right. So
and it looks like it rounds up to 3.7 times 10 to the negative 19th joules. So what's going to happen?
So close, but not.
What's going to happen is this is going to be A in a multiple choice exam, and this is going to be like C in a multiple choice exam, and you're like, yay, that's what it is. 0 points.
Yeah.
So don't do that.
Okay. So 3.6 times 10 to the.
Okay, so let's see. We had wavelength, the frequency of what was it? 5.5 times 10 to the 14th. So let's go here. Go here.
Would it be infrared?
Let's see. 10 to the negative 14th. Yep, looks like here's the 10 to the negative 14th right here. And if I take that up, I'm squarely in infrared. So that's infrared radiation right there. All right, so this time I'm being told the frequency of a photon. I want to calculate the wavelength and identify where it is. Okay, wavelength and the energy. So basically we're going a different direction. So I need wavelength. So I'll go ahead and start with 3 times 10 to the 8th meters per second. And I'm doing that because meters is the unit I want because we're talking about a length and I need to get rid of this second. So I'm going to put, so be careful with this because this is 4.5 times 10 to the 14th. And I'm going to put that in the denominator because that seconds is in the denominator. So if it's in the denominator, it actually, moves back up to the numerator. Like 4th grade division. And the seconds cancel out. And I don't know, what do we get here? 3e8 divided by 4.5 e14. So it looks like 6.7 times 10 to the negative 7th meters. All right, great. We're going to use the given frequency to calculate the energy. So 6.626 times 10 to the negative 34th joules times seconds. And then 4.5 times 10 to the 14th, and then the seconds goes in the denominator because it's a Hertz unit. So 6.626 e negative 34 times 4.5 e14. And it looks like I get 3.0 times 10 to the negative 19th joules. So not very much. What was it? It's 14th for the frequency. So it's going to be infrared as well, right? Because it's another times 10 to the negative 14. Or 10 to... Wait, what was it?
Wasn't it times 10 to the negative 7th?
No. Wait, I'm talking about frequency. The frequency is 10 to the 14th. So then here's 10 to the 14th. So again, I'm square in infrared. So it's infrared for both of those.
Wait. Where did you...
Right off the problem. Right here.
Oh, got it.
Okay, we want to talk about explain constructive and destructive interference. Okay, so what do you want to say for the constructive interference?
Um, oh, okay, so constructive interference is when two waves come together and then they build upon each other because they're both, um, like, is it because they're both equal sizes?
No, they just happen to be reaching has so they're basically in sync with each other, right? The peaks are cresting at exactly the same time. The troughs are dropping out exactly the same time. So the peaks become, the crests become double the size, and the troughs become double the size.
Mhm.
And I worded that question incorrectly, didn't I? I totally missed a
Yeah,
word.
I thought it was just constructive interference.
It's supposed to be and destructive.
I
Okay,
reworded it to say explain constructive wave interference because I thought that's what you meant.
that's okay. So we'll answer it anyway. So destructive interference has waves out of sync.
So it doesn't have to
So
do with
they
the amplitude of the wave, it has to do with
amplitude
their.
has nothing to do with it. It's the frequencies being aligned with each other, or the wavelengths being aligned with each other. Um,
So if two waves come in where it's not the peaks, but it's the valleys, I guess, then would it just also still be constructive interference?
so if these guys, so if I got another one wave like that and another wave like this, that's a destructive interference. So the green wave and the red wave are going to cancel each other out, and I'm going to get nothing there. I'm going to get just nothing. But
Yeah.
if I've got a red one and it's going along, and then the green one is exact right on top of it, the end result of that is a wave that's twice as powerful.
But this isn't light waves, right? This is like sound and water
No, this
waves.
is light. Remember,
Is it?
light is stupid. It does both.
Because I thought you said that light,
I did,
like it.
but then I also said it doesn't. But then I also said that light does what the heck it wants to do. So light
Mm,
does do this, and then it doesn't do this when it doesn't want to. But then it does do this when it does want to. Right?
yeah.
Not that that's at all confusing.
That just
No.
sounds like a moody teenager.
Yeah, it sounds like I don't know, half of you,
I'm
except
an
for the
adult.
teenage part.
Just a moody adult.
Explain why blue light can turn solar power calculator on and a red light cannot, even if the red light bulb is 10 times more powerful. Okay, so this is the discussion that we ended with last class. So I've got this tiny, tiny little blue bulb, and I've got this massive red bulb, and I've got this little solar panel sitting here, and I'm trying to get my calculator to turn on. And the blue light is sending these very few wavelengths over, and the red light is sending tons and tons and tons of wavelengths over, and nothing happens. The red light cannot turn this on. So what's the issue?
So even if we have like red light that's super large, it doesn't matter because the light waves can't build the energy that the calculator needs.
So I can answer this question in 2 words. Anybody want to give me 2 words? We okay with that?
Yeah.
So even though that there are several more red wavelengths of light hitting that, and together those red wavelengths would have more than enough energy to cause that solar cell to turn on. Since I don't get to add them together, it doesn't work. So what was our analogy with this?
The kids in the refrigerator.
Yeah, you got 30, what was it, third graders trying to pick up a refrigerator,
And then
and
two linebackers.
and 2 football players, and the 2 football players, no problem, because they have access. They can get to it. And in this case, I can't. I can't bring all of the energy of the red to bear on the electron at the same time. It's not possible. It's having two wavelengths of light hit the same electron at the same time is kind of like, I don't know, those crazy like Annie Oakley shots where she's upside down and backwards on a horse riding the other direction and somebody throws a skeet and she still shoots it. Except she's in China when it happens and the skeet's actually the size of a dust particle and she's blindfolded. So now she's not going to hit it. So they're not going to hit at the same time, so they can't bear all of their energy down onto the electron to get it to move. So this is, what was the term for this process or this thought that actually Einstein won his Nobel Prize for? Starts off with a P.
What time? Or just photo?
Photo what?
Photo.
Why is it Frodo?
Yeah, the photoelectric effect.
It's the photoelectric effect. All right, light refraction. What do we have with that? Is that the last question? Yeah. What happens with light refraction?
When a wave of light passes from one material to another and they have different densities, it bends the light.
So we'll just say this is a glass. This is air. So when it hits this spot right here, it was going in this line, and now it's going in this line. So we talked about this with prisms and whatnot. Can somebody tell me what this has to do with killing dogs in cars?
Does the light just bend in a certain way that focuses on the dog, or?
No, that's mean. So first off, what am I talking about killing dogs in cars?
When it gets hot and there's a dog in a car with closed windows,
Okay,
the dog dies of overheating.
so I guess I'm gonna do the Tesla truck.
Yeah, I was like, oh, futuristic car.
No, that's just terrible. Sorry, I'm gonna start over.
That was my time.
Looks like the Warthog from Halo.
Maybe that was what was coming to mind. So instead, we're gonna do a terrible looking Jeep looking thing. Okay, so we got this energy coming in from the sun, okay? It hits the windshield and then turns and hits the seat. So this light right here, it's visible light. So it doesn't really matter. Pick any color of the rainbow. We'll say red. So let's say some red light from white light comes through, goes through the windshield, turns, hits the seat. The seat gets, what happens to it? What happens to the seat?
It's hot.
It gets hot. How do you know that the seat's hot without touching it? Easy answer. It's hot, right? You hover your hand over the seat and you'd be like wondering if that black leather seat that I'm about to put my legs on and I'm wearing shorts, if I really want to do that. You put your hand over the top of the seat, and if it's warm, you know what, maybe I should actually touch it with my hand to see if it's going to burn me or not. So you didn't touch the seat. So how do you know that it's hot? What are you feeling?
Because it's hot outside.
No, you don't feel the heat from the outside. You're feeling the heat from the seat. So how are you doing that? What are you feeling? How about this? Is the seat glowing?
No.
No. Okay. So we're not talking about visible light from the seat. So the seat doesn't absorb the visible light and then re-radiate it as visible light. It re-radiates it as what?
As energy?
Okay, well, light is energy, so pick a spectrum.
Got it.
What? What'd you say, Sheen?
In the chat, Alice.
Oh. Yeah, there you go, infrared. So infrared, we feel that as heat. And so the seat right here had absorbed that yellow light or that red light, and now it's, I don't know what I want to use. Can you see that?
Kind of.
Let's do this.
Ah,
Okay, move over. All right, that's fine. Okay, so I'm picking this gray color because this is the energy being radiated from the seat that you can't see with your eyes, but you can feel it with your hands. So, are we okay with me saying that that's light,
the gray stuff?
the gray stuff?
Sure.
It's not visible light, but that's fine. It's still light. It's still part of the electromagnetic spectrum. So that energy comes off of there as, and it's going to be infrared light. So great. Let me erase that for a sec. Let me start that over. And so I've got this gray light. And so now the gray light comes off of the seat and it hits the windshield. And what happens?
Does it just keep going back and forth?
It bounces back off of the windshield and it doesn't go through it. So tell me what's happening inside the car.
Heat is being cycled through it.
Well, heat is entering the vehicle, and then what's not happening?
Oh, it's not exiting.
It's not exiting. So I've tried this experiment. I just took a thermometer, one of the ones that you guys have in your kits, and I put it in my car on a day that it was 58 degrees outside, but it was direct sunlight, and my car was pointed right at the sun. It was like, I don't know, 1 o'clock in the afternoon, and it was, I don't even know, it must have been like sometime during spring term, like now. And the inside of the car in 5 minutes got to 115 degrees.
Oh my god, that's crazy.
The inside of the car was 58 degrees because I opened up the doors, put the thermometer in, and let it set, and it was 58 degrees. Then I closed the doors. The thermometer was not in direct sunlight. It was underneath the steering wheel on the floorboards. And in 5 minutes, 115. How much 115 temperature can you handle?
None.
Like
Not
if
at
you
all.
were sitting inside that car, how long would you last before you were rolling windows down, open it up? Not long, right? The only thing
And the
I'll
dog
say
can't really
about
roll windows down.
breaking somebody's window to let a dog out is make sure the car's not running. Okay? All right? Because I've seen this before where a person comes out and they're like, it's a hybrid. The AC's on full. It's probably 50 degrees in there and you broke my window. That dog is asleep and happy. So before you break somebody's window, touch it to make sure that it's not cool. Like you might not notice it's running because it's a hybrid or full electric. Okay, that's it. Let's where did we? What was the last thing
That's
we?
it. So class is done.
No.
Yeah, I'll see you later. Bye.
Bye. Let me check the notes.
Kick gauge. Okay, so looks like the next thing we needed to talk about was atomic line spectra. Because we were talking about photoelectric effect and whatnot. So the next thing we're talking about is atomic line spectra. You actually see this all the time. You don't know it, but you do. So this is also a way that we can identify. This is how we identify what atoms are in what substances. This is a way to do it. This is a very good way to do it. To know what atoms there are. That doesn't necessarily help us out with the molecules that might be there, but I can absolutely tell you if a particular atom is there or not. Okay, so first off, this is a hydrogen atom, and how do you know that?
In the middle?
The whole thing.
The whole thing? Yeah.
There's one plus charge in the middle. The only thing that has a plus charge in its nucleus, one plus charge in its nucleus, is hydrogen.
Hydrogen.
So let me jump back and bring something up from the other class that we talked about before. Oh, you know what? I can't. I have to bring it up in Word because stupid Note won't work. Are you guys seeing this Word document?
Yep. I remember that.
Okay, so do you remember these? The energy level diagrams? And this was an
Um,
energy level diagram that was big enough for all of the atoms on the periodic table. And we know
Yeah.
that because the biggest atom on the periodic table is in the 7p. And so there's my 7p up here. Okay, so let's talk about something. What atom do I want to do? Let's do potassium. So, how many electrons does a potassium have? Because I know you're sitting there with your periodic table.
Listen. Oh man, did I? Potassium has 19. I feel like that's the wrong number.
That's right.
But alright.
Okay, so we have the electron configuration is 1s2, 2s2, 2p6, 3s1, 3p6, 4s1. And we know it's 4s1 because it's in the fourth row on the periodic table in the first column in the s block. So potassium is super reactive because it's got that one electron that it doesn't want. It's trying to get rid of that thing. But the potassium element itself, you don't necessarily need, well, forget about it. That electron is super reactive. So if I take that and I pack it into something and all I really need to do is heat it. If I get it really hot, what I get is the electron will start doing something that it doesn't want to do. So right now I'm going to say that these electrons, these 19 electrons, are in ground state. Do you remember what that term meant?
They're not reacting with anything?
No,
They're in the state of matter known as ground.
no.
No, they're touching the ground.
The electrons are as close to the nucleus as possible.
Right.
Alright.
Oh,
So,
and then
this
whenever we put
this
it into
is-
it, they start jumping out.
This is you on the merry-go-round. So if I've got 19 people on a big merry-go-round and the thing is spinning, remember we showed that thing with the motorcycle and the merry-go-round and the people getting thrown
Yes,
off of it?
yeah.
So imagine we've got like a machine and the merry-go-round is going really fast. Where do you want to be?
You want to be in the center.
No, you want to be not on the merry-go-round.
Yeah.
But if you're on the merry-go-round, you want to be as close to the middle as possible, right? So what we have are 19 electrons around this potassium merry-go-round, and so they're trying to get as close to the nucleus as possible. So if I add energy to it, this electron right here is going to jump. Let's say it jumps up to here. Okay, so I added it via heat or light or electricity or something like that. Well, does it want to be up there?
No, it wants to be in the center.
No, it doesn't want to be in the center. It just wants to be as close to the nucleus as possible. We okay with that?
Yeah.
All right, so this electron will jump down. It might jump all the way back down to where it was before, but probably not. What it's probably going to do is, say, jump to there, and then maybe jump to there, and then jump to there. That's fine. When it falls back down, all of the energy that it took to get up to that 5D where I'm shown comes back, whether it's in one jump or whether it's in 3 jumps. And that energy comes off in the form of the electromagnetic spectrum, so light. So light, light, light coming off of here. You okay with that?
Mm-hmm.
Some of this is going to be visible light. Some of this is not going to be visible light. So if I had taken this and packed it into something, surrounded that something with gunpowder, and launched it up into the sky with a fuse, and then the gunpowder ignited, what am I looking at?
Firework.
I'm looking at fireworks. And this is how fireworks function. They take elements that are in their ground state and they throw them up into the atmosphere with usually gunpowder, and then when it ignites, those electrons get excited, they jump out of their ground state, and then they fall back down to where they were before. So sometimes it's just one electron that falls. Sometimes it's several electrons that fall. And whatever the color is, it's a combination. So in the same way that if I put yellow and blue together, I get green. If the colors that come out of the atom are blue and yellow, then the color that I'm going to see is green. Does that make sense? It might just give a straight green color, and then that's it. And so I'm looking at an actual wavelength that's green, or I'm looking at a combination of a bunch of wavelengths that are all released at the same time. Does that make sense? So let's hop back over. No, not that. Let's hop back over here. So that's what we're looking at here. So we're doing the most simplistic one, which is the hydrogen atom. So what we're showing here is the hydrogen atom just has one electron, and then it says N 1, 2, 3, 4, 5, 6, and 7. Those are the energy groups, the principal energy groups. So principal energy group 1, 2 through 7, and we know how many there are because the periodic table has 7 rows on it, right? So it corresponds to each one of those principal energy levels. So what we're saying here is if I've got an electron, we'll just pick a spot. So I'm going to pick this spot right here. Not that color, though. So what we have is an electron right here, which is, what is that? N equals 6. That's where this electron is. And if this electron at N equals 6 falls to N equal 2, you actually get green light out of this. All right? Why would I get blue light if I'm falling from 7 down to 2?
Longer wavelength.
More energy. Allison's right. It's a farther fall, right? So since it fell further, it gives back more energy. And blue has more energy than green does, so it gave back a wavelength of light with more energy in it. So what if I fall from N3 to N2? Didn't fall very far, right? So I'm going to be giving back red color, which is the least of the electromagnetic spectrum that's visible. So what if I'm falling from 6, but I only fall to 3, and I don't fall all the way down to 2? Then I'm going to be giving infrared. So anytime you fall down to this 3rd energy level, I don't fall enough. That fall isn't far enough to give me anything other than infrared light. But what if I fall all the way down to the 1st level?
Then you get, do you get ultraviolet?
I get ultraviolet light. So if you go to a tanning booth, the radiation that's coming out of those bulbs has to be what kind of radiation?
Ultraviolet.
It has to be ultraviolet. This is what's happening. So they put substances inside of the light bulbs that when electricity runs through it, it causes the electrons to jump up to a high energy level. And when they cascade back down to where they were before, they produce a bunch of light that is in the form of UV. And so you get hit with radiation that is actually harmful to you. But it also does something else. What's the whole reason it's trying, what are you trying to do with that?
Ultraviolet?
Yeah, why are you purposefully exposing yourself to a type of radiation that can cause cancer?
You get a tan.
So your body sees, hey, that can give me cancer. So then that causes tyrosinase to become activated. And when that enzyme becomes activated, it causes another molecule to produce melanin in your skin. So that's what we're stuck with. So what you see here is there's a visible light. Sorry, say that again.
I just not go outside.
Or you could not go outside and, I don't know, drink a lot of milk with fortified vitamin D in it.
I don't know. Nosferatu did it.
So depending on from what level to what level you fall, you're going to get different amounts of radiation energy-wise based off of, the distance you fell and from what level to what level. So just dropping from one level to the next doesn't necessarily tell you exactly what you need to know. You need to know, did I fall from 6 to 5? Or did I fall from 2 to 3? Or did I fall from 2 to 1? That definitely matters. Okay, so are we okay with me showing this ground state, excited state thing?
Yeah.
What element is this?
2, 4, 6, 8, 10, 12, 13, 14, 15, 16. It is sulfur.
You're right, it is sulfur. And so on the one on the right-hand side, for some reason, one of those sulfur's 3p electrons has gotten bumped up to the 3d. And that took energy. And then when it falls back down to where it was before, what's going to happen?
Or light is produced?
Some kind of light. It could be visible light. It could be not visible light. So those are your two options.
So
Okay.
how are we supposed to tell the colored light that is produced based on the fall?
You can't.
Oh,
You can't figure it out, meaning you can't look at the atom and determine what the fall is. Let me rephrase that. Sorry. We can for hydrogen, and that's it. We have come
because
up with
we
an
have that
equation.
graph.
We've come up with an equation for two objects, a nucleus and an electron. If I put a second electron in there, and now I've got a three object something or other, it doesn't work.
Okay.
We figured out the hydrogen atom calculation Heisenberg's time, like 80 years ago. And for the last 80 years, we've been trying to figure out how to use a calculation for all the rest of the atoms. We're
Yeah.
still waiting for somebody to come up with that. So what that tells me is we don't know what the hell's going on, which is fine, but we will
Typical.
eventually. We just don't yet. Okay, so here I've got the entire rainbow, right?
Yeah.
So if I take all the elements in the universe and I put them into a gas ball and I heat that gas ball up to a high temperature, what colors do I get? Those colors. No, these colors here. I get all the elements in the universe, give me the entire rainbow. But if I just take hydrogen and I just put hydrogen into a container and I run electricity through it, I get those four colors, and that's it. Those are the only four colors. Together, they give like a.
Purple.
Can you guys see Jordan's curtains? Here, let me help.
Where's Jordan?
Can you see Jordan's curtains?
Magenta.
So it's like that, but more faint.
Okay.
So that combination of colors, in the same way that if you take a color palette, you can make whatever colors that you want. Those four colors right there give that pinkish kind of color. And it's not just the colors that get mixed together, it's also the intensity. So in this case, the red is more intense, meaning it happens more often than the three different blues, or the looks like two blues and a purplish. So this is the atomic line spectra for hydrogen, meaning if there's any element, if I've got a substance and there's any hydrogen in it at all, if I put it in a flame spectrometer, I will get these color lines.
I think I've done that before in
You probably have. You guys actually did this in the separations, or no, the lab where is it a chemical reaction or is it not a chemical reaction? And you took sodium and you put it in the flame and it was orange, and then you dissolved it, and then got rid of the water and put the sodium back in the flame. Sorry, not the sodium, but the table salt back in the flame, and you got orange again, telling you that it wasn't a chemical reaction. So you've seen this. So if you're able to do that with hydrogen, I mean, you can't put it on a stick and put it in the fire because it's a gas. But if you trapped it into a bulb and did this, you would get those four colors that equate that pinkish color in Jordan's curtains. This is neon. The spectrum on the right is what colors neon forms, and the color on the left is the tube that you would see. So if I put neon in a tube and turn the electricity on, that's the color. So when you think about a neon sign, that's a neon sign, meaning neon gas was put into this tube and electricity was run through it. So this is really exactly the same kind of bulb as the regular fluorescent light bulbs that you probably grew up with in grade schools and middle schools and high schools, because those bulbs were the most efficient. They're not anymore, but they have been for a long time. But if it was neon in there, you'd get that color, which probably wouldn't go very well in, I don't know, in your math class. But it's interesting because there's a bunch of colors that are really close to the color that it is, but then there's also those greens. So how come there isn't really any green color in the overall color? If you were mixing palettes of colors, okay, and you put, I don't know, like a cup of orange paint into a bowl, and then you put a teaspoon of green paint into a bowl and a tablespoon of yellow paint into a bowl and mix it together, are you going to be able to see the green?
No.
And that's what's happening here. The green is being overshadowed by the reds and the yellows and the oranges to give that color. So this was the first bulb that people used in this manner. So before there were the fluorescent bulbs that you guys are used to, somebody made this into a sign. It was for a Chevrolet dealership in California, and I don't know how much they paid for it, but it was the first one in existence. So my guess is it was expensive, but it was also like a talking point. Like, did you see that new sign down at the Chevy dealership? If you've never seen one of these signs before, it's a little remarkable. Like, you're going to talk about this. Obviously, now you can get them anywhere and they're all over the place. But when we talk about a neon sign, we use that term in a general sense, meaning any of the signs that have this kind of aspect. But you've seen this before, and you probably called a neon sign that was maybe green or blue or some other color, and you still called it a neon sign. It's not technically a neon sign. It's like calling a copy out of a copy machine a Xerox. Like, technically, it's only a Xerox if it actually came out of a Xerox machine. So if it comes out of a, I don't know, an HP copier, then it's technically an HP copy, but people still say Xerox. So how come I get so many different lines here? Up here for the hydrogen, I only had the 4 lines. How come I have, I don't know, more than a dozen lines here?
Because it's bigger?
Not, it has more electrons is the issue. So the hydrogen only had 1 electron. It could only go up to certain places and come back down. But the neon has 10 electrons, 8 of which can bounce around, 8 of which are in energy level 2. So those 8 electrons going up to different places and then coming back down to their ground state, releasing all of these different colors. You okay with that? Anybody have any questions about that? No?
Why is there like a little flare on that big orange line?
This one right here?
No. The
Here?
line, yeah. There's like a giant flare at the top.
Oh, it's just where the bulb makes contact with the electrode.
Oh, okay.
It's like it's got, the ends of this are probably 2 centimeters in diameter, and the tube portion of itself is less than a centimeter. So it just extends at the ends. If you can see the ejections, see the color, then it's called the Balmer series, because this was the scientist who first discovered that. And the visible series is the series that we call it if we can see it. The Balmer series is the ultraviolet, and the Passion series is the UV light, the
Where do the
infrared
names
light.
come from?
Balmer and Pash are just the guys who said, hey, yeah, we have a spectrum for visible. I wonder if it's producing light that's outside the visible spectrum. And they're like, yeah. Sheen asked me a question before you guys got here and was asking me, like, how do you produce X-rays without doing electron capture? If I have a particular element and I hit it with a certain amount of energy, instead of getting UV, I can actually get X-rays. So the fall is powerful enough to give me X-rays, depending on which elements I'm talking about.
What's the upper limit on that? Or can you produce basically all forms of EMF radiation?
You can produce all forms of, well, let me rephrase that. You can produce everything above some radio. There's some low-level radio waves that you can't produce because the fall is more energy than that. So if I'm looking at this spectrum way up here, we'll get there eventually. So some of the stuff that's down here I can't produce in this manner because the fall is so big that it produces more energy than these long wave of radio. But the rest of them you can produce.
What would cause something to produce gamma rays? Like what specific part of like the nature of it enables it to do that? Just size?
Just size. Yep, size.
Weird.
When I'm thinking about these falls, the analogy that I can think about sometimes is if you're standing on a step and you jump off the step down to the ground. If you're on the first step, like that jump isn't a big deal, right?
Mm-hmm.
But what about if you jump from the second step down to the bottom, or the third step, or you skip the staircase completely and jump like 12 stairs all at the same time?
But you get that feeling whenever your feet hit the ground where it like feels like energy just rushes up your entire spine.
Yes, I agree with that. 10 feet, that's about 10 feet, and that would be painful unless you were falling on something that cushioned the blow for you. But if you're falling on concrete, that's not going to feel good.
Series,
Yes, go ahead.
in the visible series, is it showing the light going from level 7 to level 6 to level 5, or is it just showing?
It's showing a straight jump from like 6 to 2 or 7 to 2. They're all falling down to energy level 2 in a straight shot. It's not sequence where they go 6 to 7, 7 to or 6 to 5. It's a straight shot.
Okay.
Here's the equation that we were talking about works for hydrogen and doesn't work for anything else. We're not actually going to use it because I think it's great. Yeah, we got the equation and it works for hydrogen and nothing else, so it's sort of useless. But the N's refer to the energy level that they're in. So if I'm in energy level 6 and I fall to energy level 4, I can put a 6 in for NF, sorry, a 4 in for NF and a 6 in for NI. Square them, do the subtraction, and divide that into the Rydberg constant, which is that number up there, and then I get an energy. And that energy.
What's the E?
What? Energy?
Oh.
If I know the energy of the photon, then I can figure out what the wavelength is going to be and what the color is. But again, it only works for hydrogen. Okay, so
you want to have a question that's like, this is hydrogen. What would happen if it jumped from level 7 to level 2?
probably not, because I don't really care about that equation. Okay, so we're going to talk about this because this is kind of interesting. It might be important to us in I don't know how many years, but it doesn't really matter. So first off, this is the emission spectrum for sodium. The one that's black with the 2 yellow lines, that's it. That's the entire emission spectrum. It only gives those 2 lines of yellow, nothing else. You've seen this before. Can somebody tell me where this applies in everyday life?
I've seen it in astronomy, but I don't know in everyday life.
Nobody?
Oh.
So, we okay with this color here?
Yeah.
We've all seen that many times, right?
Mm-hmm.
Why is the street light this color? Why is the street not light white?
Because it's sodium.
Because it's sodium in there instead of, say, tungsten. So when I was 10 or so, the people that lived in our neighborhood had we didn't have like an actual, those homeowners association things didn't exist, but somebody went around all the different houses and said, hey, we would like street lights on our streets. We're going to have PG&E come to a meeting at the grade school, and we'd like you to come down and we'll talk about how much it's going to cost. So what it turned out was we could have white street lights in our neighborhood, or we could have sodium street lights in our neighborhood. The installation cost was going to be the same, but then the maintenance to pay for the electricity was about 100th for the sodium lamps. So basically what they were saying is your electric bill is going to go up. I don't even remember what it was. This was 1980. So it was going to go up like $1 a month, or it was going to go up like $4 a month, something like that. And so everybody chose the $1 a month. So we got these sodium lamps. So why are the sodium lamps? First off, they produce that color because this is the emission spectrum. So I put the sodium metal inside the lamp. I run electricity through it. They heat up. The electrons get excited. And when they fall back down, they give yellow and yellow. And that's all you get. But it's phenomenally efficient. So it absorbs a ton of energy, and you know it absorbs a ton of energy because where else have you seen this color? What else is this the color of? Man, I cannot make this thing bigger for the life of me. How about the lab you did with the sodium? What color is that? What does it look like? The color of what? Flames.
Oh,
What color are flames? Unless I'm talking about burning something specific. There you go.
Yellow.
There's that color, there's sodium around. The sodium overpowers everything else and produces that yellowy color, which is why sometimes you can look into the fire and see a little bit of blue or a little bit of red because there's some potassium down there, or there's some cobalt down there, but not very much. So the color that you're getting is the color of those electrons from the sodium going up and falling back down. All right, so
What is this thing?
it's a bug.
It's really big.
Looks like a cricket to me.
Yeah, that's what I thought, but it's some sort of beetle.
Spider.
I don't know. Jules?
No.
Is it a cricket?
Or Madeline.
Nothing. Nope, that's a
It's a
kissing
beetle.
bug.
It's a kissing
Yeah.
bug? That's cute.
Yeah,
I'm gonna put
if
him
you look
down.
really closely, you can see little proboscis there. It might bite you.
Oh, I'll put him down. Well, he's been very active all morning.
Okay,
There
so
you go.
if I take my sodium and I put it in a lamp and I turn it on, and in between the sodium light that's being generated and the detector, I put a gas cloud that has all the elements in the universe in it. The cool thing that happens is the sodium color gets absorbed. So that's what this spectrum is right here. Instead of me just seeing yellow, what I'm seeing is I'm missing the yellow. Okay? So, great. Who cares? The reason that this is important for us is, let me do it like this. You know, typical terrible drawing coming. All right, so I got a planet here. And around the exterior of the planet, there's an atmosphere. And way over here, there's some foreign sun that's behind the planet. And way over here, super far away, here's Earth. Okay? So this sun is producing regular white light. And it goes through this atmosphere, and then it comes to us. Minus some wavelengths. So why is this interesting?
Hence it to list the composition of that atmosphere.
So whatever this atmosphere is, let's say it's O2 or N2, or let's say it's arsenic. Those elements all absorb light at a certain frequency and certain wavelength. So if the wavelengths that are missing are the wavelengths for arsenic, we don't want to go there. That planet's atmosphere is gaseous arsenic. Seems bad. But if the colors that are missing are the colors for oxygen and nitrogen and nothing else that's going to kill us, then maybe that's a planet that we could go to. And again, I said this was for way off in the future. So when you read things about there's a habitable planet in the Goldilocks zone with an acceptable atmosphere, you might say to yourself, how in the hell do they know what the atmosphere is? It's light years away from us. There hasn't been a probe there. This is how we know. Because by the time the light gets to us, it should have all of the spectrum, the full rainbow. And the colors that are missing tell us what that atmosphere is composed of. We good with that? What else with this? Anybody have any other questions about the spectra? Interesting, tell Elon. Elon knows about this, but he's not considering things further away than Mars right now. Does this apply to supernovas and why they're colorful? No. The reason that they're colorful is because they pass through gases on the way to us. So depending on what color the supernova is, that will tell you what gases are in between us and that supernova. So if you're looking at things like the Horse's Head Nova, Crabshoe Nebula, all those different astronomical entities. The reason they're the color they are, for the most part, is because there are certain gases in between us and them. Which is why when we're looking at stuff like that, it's best to have the equipment that we're using to be outside of our own atmosphere.
I found it. Douglas fir borer.
What?
It's a longhorn beetle. Douglas fir borer, like it bores.
Oh, you should kill that
Why?
because
Oh,
it kills
yeah.
Douglas fir trees.
Yeah, but he's
No
He's a
buts.
really small borer. Those are usually huge.
Yeah, well, he's a big beetle in general, but
No, look at her fingers.
I mean, they make a noise when they hit.
All right, it's 3:30. Let's take 5. I'll be right back.
okay, I get to examine the beetle. He's on my water bottle. Hello.
Tell me.
Can you see
I have
it?
to see him.
Can you see him?
No. Are those antenna?
Huh?
Really, really, really long? Are those antenna?
Yeah, no, his
Mhm.
antennae are about like, I'd say almost an inch long.
Yeah. Well, that's what I was thinking. But those beetles have pretty long antennae, but I think they're frilled. Are these right?
They're not frilled, they're very smooth.
They're smooth. Let me see here.
I kind of want to handle him, but also, like, I don't want to get bitten or anything.
Okay, so here's a family of beetles that it probably belongs to.
I'm trying to get him back onto my pencil. Come on.
I'm gonna go in there and see what we can find out. So, 28.
It almost looks like he's like searching for something because he keeps sniffing stuff.
Sniffing?
Like he'll lower his mouth to the ground and like almost touch the mouth with his ground or touch the ground with his mouth.
So, are his antennae doing this? Or are they straight outward?
They're okay. First of all, his antennae are like bouncing up and down, and they're pretty much straight, but they curl just a bit at the top.
So pretty much straight.
Yeah.
Because you know that's what antennas are, just taking in information.
Yeah.
So I'm not saying it's not a kissing bug, so I'm wondering about that.
Yeah, I'm not touching him. But the bug that I found online that looks most like him is Centrodera spurca, or spurca.
People
He's very cute.
bark or what you call it. So did you look at the size? Did it give you a size, a length of the whole like body?
The one it's giving me is like the length of about a little bit more than a penny. I assume that he's about as big as a quarter. Also,
So
I'm pretty
if
sure
it's
he can fly.
the size of a penny. That makes sense.
Yeah,
Oh yeah,
I'm
that
pre-
definitely fly. Oh, beetle can fly.
since
You
he
know that?
flew in. No, I actually didn't. I just don't want him
Yeah.
to fly on me because I've got a lot of hair that he can get lost in. He was on the windowsill and he just
I don't
straight
think he's into your hair.
no. But he was on the windowsill and he walked straight into like a really old spider's web and just walked through it with no problem. He didn't get stuck at all.
He's not in your character, I don't think, but how about whoops. So for the length of the antenna and the shape of the body, are we closer to this?
The body shape is not like that. The body shape, his shape is almost like a pill, like just a straight pill. It's really smooth. There's no patterns or anything.
Does he have a head?
He does
and
have a head.
thorax?
It
Does he
looks
have a
like he does.
thorax?
It looks like he does.
Okay, then yeah, you're right. It's meant for placebo.
Yeah, he's doing the thing again. His little these guys are like rattling when he touches
Touches
them.
up on trees.
Huh?
You live around conifer trees.
We've got 2 big pine trees right outside my door.
Let's do that.
His little pincers are
Seems like
rattling.
a
It's so cute.
So
Oh my gosh. He's got
as
personality.
cute as a
Spiders aren't cute to me. I don't know. I've always been kind of grossed out by them. They're interesting. I like to draw them, but
yeah, they're interesting to draw.
I don't know. They always give me the heebie-jeebies.
Speaking of creeper crawlers, we found a danger noodle outside the other day.
Oh, those I love snakes. I love snakes.
Yeah, I think I can find the picture somewhere.
I have a ringneck boa that got loose in my house. Or not a ringneck boa, just a ringneck snake, and he got loose in my house, and he was just kind of like a roommate for a while. But since I don't smell a corpse, I'm fairly certain he got out into the wild.
There he is.
There he is.
Wow.
Wait, man.
What?
I ended up getting a shovel, and I scooped him up and put him in the back.
Nice.
Machine.
Do you think that they're still in the area, or they just got around and are somewhere else?
Well, there's actually because my house isn't like a real house, it has this hole in the floor in the kitchen, so he can totally get out and like get to the outdoors. So I think that's what he did. But he probably
What do you mean there's a hole in the floor in your kitchen?
it's nowhere I can reach it, and it's nowhere I can really do anything about it. It's
Is that where you put the dead bodies?
no, I wouldn't put that in my house, Rob. I live in the woods. There's so much available space.
You lose your snake. What do?
Good
Do you
point.
put like salt down or something?
Well, he's
Pinkies.
next to Oregon,
He's
so I
so
don't
curious.
know if he wanted to go. Gotta
Yeah, I've seen some people like if their snake gets out, they put like a line of like flour or salt, so you know when they cross it because you see the line on it.
Wow.
water is also a good thing. It's like a little tray of water. They'll prove it.
Mhm. And if there are ones that like to hide in like little small spaces, makes it even worse.
All right, let's move on. So we've done a couple of nuclear equations before, but the ones that we had were pretty simple. Maybe 3 things total. Here's one the first one has 3. That's beta decay of carbon-14, the radioactive version of carbon, and everything in the superscript adds up. So 14 equals 14 plus 0, and in the subscripts 6 equals 7 plus a -1. So we're good. The next one shows carbon-14 plus a hydrogen atom being absorbed into it to produce nitrogen and a neutron. So on the top, we've got 14 plus 1, so 15. And on the other side, we also have 14 plus 1. So the masses are okay. And then for the proton number in the subscripts, we've got 6 plus 1 is 7, and the other one is 7 plus 0 is also 7. So those numbers have to end up balancing out. Okay, so the next one, we've got a very important reaction. Neutron goes into a uranium-235 atom. For a moment, it turns into uranium-236, and then it splits apart into rubidium 93, cesium 140, and something we haven't seen before, which is a coefficient in these. So this is 3 separate neutrons come flying out of this. So when I'm adding these things up, this one's pretty easy. This is red color. That's 236. That's 236. And then this 93 and 140 plus 3 times 1 gets me up to 236. You okay with that? So why is this reaction important? This is the reaction for nuclear power plants. This is the reaction for the first bomb that we dropped on Japan. And the person who came up with this equation was a woman named Liz Meitner. She's a female, one of the first female physicists, really ever, at least accepted in Western society. I don't remember if you guys remember this guy here. He was the person who talked about microstates.
Oh yeah, Boltzmann.
So this is his tombstone.
It's scary.
Doesn't look super friendly, does he?
No.
So he had a conversation with Meitner one time in a basically in a bar with a bunch of other scientists, and decided that she was the smartest person in the room other than him, obviously. And said, "Hey, do you want to come work for me?" And the other guys in the room kind of laughed, like, "Haha, yeah." And he's like, "No, she's gonna come work for me." And then when they said, "You can't hire a woman, you can't put a woman in your lab," and he's like, "I'm Ludwig Boltzmann. I can do what I want. Period." That's this is basically was almost a quote of what he said. She's the smartest person in the lab, so I'm gonna hire her because she's smarter than you are.
Ooh.
And then another night in a bar, she wrote this equation down on a cocktail napkin, and it turned out to be correct.
The 235 to.
Yep, the 235 turning into the rubidium and cesium.
Nice.
And we're definitely going to talk more about that reaction here later. What's the prefix trans mean?
Become
No,
or change.
no.
Across.
Across or past, like transatlantic flight. So this is elements that are past uranium. So everything that's past uranium, so neptunium, and then all the way out to, I can't even pronounce 118. Somebody do that for me. Oz something or other, or Oganesson or something like that. All those elements are elements that we've made. So when somebody says something about a transuranium element, they're just talking about the elements that are past uranium on the other side of the table. And all of those elements are not natural, meaning we've created all of those. I mean, most of them are kind of like, do you know the names of any of these elements past uranium?
No.
Yeah, you do. You know one.
Oh.
Plutonium.
You know plutonium. But outside of that, you don't know the rest of them. We talked about americium a couple of times being in smoke detectors, and we'll talk a little bit more about that later. But the rest of these, they're just named after famous chemists and physicists. There's we've had zero ability to use any of them. So why do it?
Better understanding.
Yeah, absolutely. Because we don't understand how to calculate what the emission spectrum is going to be for any other atom than hydrogen. So maybe this will help us. Okay, so I want to talk about field effects. So the two field effects that we can introduce there, we've talked about these before. They're a magnetic field and electric field. This is the reason that the neutron wasn't discovered for a long time, because it is unaffected by field effects. So if I take a little bit of radiation, some radioactive material like pitchblende or something like that, which is a rock that has uranium in it, it's sitting in this lead block, and the reason I'm doing that is because it can't get through the lead block. So it's just going down this little portal here. And I set up an electric field, and when I do that, we're going to find that the radiation that comes out of here is actually composed of beta particles, gamma rays, and alpha particles. So how do we know this? I got a little detector here, and this detector can test for things that are positively charged or negatively charged. And it can test the mass based off of how far the particle penetrates into the object. We okay with that? So, is there anything you want to talk about or ask me questions about this? I didn't draw this, so it's drawn correctly. Does any of it, is it confusing? Does it make sense?
Yes. Okay. I mean, yeah, it makes sense. If
Why does the
because it's
beta
gonna-
particle move up?
Is it because it's lighter?
No?
What do the colors represent?
Nothing.
Because they have more energy?
This isn't like up and down vertical. This is fine to just say this is the left side and this is the right side. So why did the beta particle turn left? As it passed through this gate, why did it make a left-hand turn?
Because is it because it's being attracted by the positively charged side of the electric field?
Why?
Because it's negatively charged?
All right, so the beta particle is negatively charged, so it makes a left as it goes through the field. The alpha particle is positively charged, so it makes a right going through the field because this is the negative side. You should be pointing something else out though.
The gamma rays don't?
Okay, fine. The gamma rays don't because they're light and they're not a charged particle at all. That's fine. But you should be pointing something else out.
The alpha particles are.
The alpha particles
Oh,
are
the
weird to the right,
space!
left.
There's a different amount of space between the gamma and the alpha and the beta and the gamma.
The alpha particle didn't veer as far off to the right as the beta particle did. Tell me why.
It's got less of a charge.
The beta particle has less of a charge, but that doesn't make any sense, right?
Is it because the alpha particle has significantly more mass? So it's got kind of like inertia almost?
That's exactly right. This guy's mass is
Oh,
1/18
inertia. Guess what? Physics.
1/18,000th of an AMU. Because it's just an electron, right? What's this guy's mass? 4 AMU. So how much smaller is this thing than that thing? 70, what is that? 7,600 times? 7,400 times? We okay with that? So what has better traction on the road? A Porsche Boxster or a garbage truck?
A garbage truck.
Which one is going to make a corner better? The Porsche
The
Boxster
Porsche.
or the garbage truck?
The Porsche.
But you just told me that the dump truck had better attraction to the ground.
Okay, by turn, do you mean a faster turn?
Yep, a
or
faster turn. Yep.
Well, since the Porsche has less traction, it's able to move faster.
That doesn't make any sense. Anybody else?
Traction slows you down. Traction, friction.
The center of gravity of Porsche from the dump truck.
I'm sorry, say that again, Ronald.
The center of gravity, or how low it is to the ground
No,
compared to the dump truck.
that's minor by comparison.
No,
I mean, what's the obvious answer?
it's faster.
Okay, so
Heavier.
are you okay with me saying that a dump truck and a Porsche Boxster can both drive 50 miles an hour?
Yes.
I know they do because I live on Highway 35 and the dump truck goes past our house at like 70.
Oh God.
So when you're driving down from Parkdale down to Odell, there are some spots where you probably should slow down a little bit if you're driving over the speed limit. Why does the Porsche not need to slow down? Sheen,
It's a lot lighter.
it's a
So
lot
there-
lighter. That's
you
it.
said the Porsche, didn't you?
The Porsche is a lot lighter, right? So even though the truck is, I mean, what are you worried about when you're going around a corner? You're worried about your car sliding, right?
Mhm.
Well, the truck isn't going to slide as easily because it's got more tires on the ground, and the tire touching the ground is what's giving the friction. But the Porsche only has 4 tires, but it doesn't have to turn as much around the corner, right? You okay with that? Like small wide receivers in the NFL can turn a lot better than large offensive linemen can, right? Even if they're running at the same speed, and then they go to turn, the offensive lineman can't turn quite as well as the wide receiver can because there's too much inertia going. So when we're looking at this, that alpha particle, even though it's more powerfully attracted to the negative because it's got a +2 and the beta particle only has a -1, it's more than 7,000 times more massive, so it just can't take the corner as fast. You okay with that? Same exact situation happens with the magnetic field. It's just instead of it being an electric field, it's a magnetic field. So the beta particle would be skewed much, much greater going through the magnetic field than the alpha particle would. I used to have this little box here on the right. We used to talk about this for a while because everybody knew what a CRT television is. But I mean, it's been 10 years since it's been longer than that since I've even had one. So,
Is there anything interesting you can do with those? Because I may or may not have a few of those monitors and no use for them.
yeah, there's no use for them. So these are CRT televisions. The reason they're big is because they have this thing here that shoots electrons to the back of the piece of glass that's got a paint on it that when the electron hits it of a certain speed, it gives it a particular color. So you can get all the colors of the rainbow and see everything. But we don't make TVs like this anymore. We just have tiny little, basically very, very small LED lights that can hit red, green, or blue. And then we just tell it what color to go. And then we've got all the colors of the rainbow. And I mean, who's moved one of these TVs besides me?
Me.
I mean, I had a 32-inch TV, and that thing weighed 132 pounds. That's not funny, right? Walking up a staircase with that, and if you drop it, that there goes $600.
Yeah, I remember seeing something that said talking about how nowadays when we put TVs down, we don't want to break the TV. But back then, you put the TV down carefully because you don't want to break the coffee table.
Yeah, or your foot.
Yeah, or your foot or anything part of your body. It's heavy.
Okay, so I'm just going to start off by saying I'm sorry. I had nothing to do with this, but
Here we
this
go
is just the
again.
way it is. Okay, so we talked about this before when we talked about units for gas laws, right? I'm sorry that there were a dozen of them. I'm sorry that there are all these stupid units for radiation. But you could see any of these, so we're going to go over them briefly, some of them, and then talk about the ones we really care about. So the first one is Becquerel, and it's named after Becquerel because he was one of the first people to recognize radiation. The next one is called Roentgen, and that's because the other guy who came up with, hey, radiation is a thing, that was his name. So these 2 units get named after him. The first one is almost completely useless. 1 disintegration per second is dumb. Why? Because when I've got something that's radioactive, I'm having billions of nuclei decay per second. So 1 disintegration per second is not a usable number. The Roentgen is an actual wholehearted usable number, and it's very important to us. So there's 2 versions of it. One in dry air, and the other one is in tissue. So one of them produces times 10 to the 19th ion pairs, and the other one produces 10 to the 12th. So are we talking about a billion, right? 2.1 billion versus 1.8 trillion ion pairs. So what's an ion pair? What do we mean by that? Let's back up 2 days. What causes cancer? How does radiation cause cancer?
It breaks the cells. No, it disrupts the nuclei whenever they're
No,
in
no,
mitosis.
no, not. Oh, nuclei. You mean nucleus of the cell?
Yes.
You need to be more specific than that. It breaks a chemical bond. The only way to cause cancer with radiation is to have a bond, a chemical bond broken. Most likely a bond between two carbons, or possibly between a carbon and an oxygen, or a carbon and a phosphorus. That's how you get, or a carbon and a nitrogen. That's how you get cancer from radiation. So when that happens, I break a bond, and now I've got two pieces that are both charged particles. They're ions. We okay with that? So what this is saying is 1 roentgen of energy will break apart 2.1 billion chemical bonds. That's and you've got a roentgen, and that's in air. And so if I'm talking about shooting a roentgen versus of radiation into a dog or your thigh, then you're actually going to get 1.8 trillion bonds broken. What's normally going to happen when the bond breaks in the cell?
Then the cell dies and then it doesn't replicate.
Correct.
Likely.
Most likely dies and doesn't replicate. And so this is happening to you right now. It's happening to you constantly. And most of the time it doesn't matter because it just kills the cell as opposed to allowing it to reproduce. But the more times these bonds get broken, then the more chances that the cell doesn't die. So the second number is a little bit more important to us because we don't so much care about what happens to air. What we care about is what happens to our own tissue. Okay? The next unit is important because this is about the amount of energy absorbed basically by inanimate objects. So if I'm talking about like a pipe or a piece of shielding or a valve or something like that, it's going to absorb radiation in units of rads, and that's 0.01 joules of energy per kilogram of material. And so that's where the rad comes from, the acronym radiation absorbed dose. And why would this be important for us to understand how much radiation a particular object can absorb before bad things happen? Because if I build a nuclear power plant and the valve that's getting hit with radiation fails because of the radiation it gets exposed to, and then the nuclear power plant either is not functional or has a serious problem, I would like to know that kind of stuff. So before you use any materials in a nuclear power plant, it gets exposed to a great deal of radiation to see how long it can last with that radiation absorbed into it. You okay with that? So it's not like they're not making valves out of stuff that you can buy down at Bryant Pipe Supply. The valves that they use and the pipes that they use, they before they get put into service, they actually get gamma rayed. Radiation goes through it and they're checking for interstitial defects. Do you remember when we were talking about what makes steel stronger? You could beat on it, you can add impurities to it. So you take gamma ray images of these pipes of the entire system, and the system is incredibly elaborate because you want to make sure each and every one of those pieces can withstand being hit by radiation. Gray is the next unit, and although it's the official unit for the metric system, for the SI system, I've never heard anybody ever use it. And I was in a nuclear power plant on the aircraft carrier. And my master's degree is in nuclear chemistry. I've never seen this written in a paper, so don't worry about it. But it's actually the official unit. The next one is the most important to us. Why?
Because it has to do with joules.
No. Joules. No. The next one. Because even though it's a little sexist by saying just man, it's talking about humans. So we really care about this one because we want to know how much radiation a human can absorb before bad things happen. So this radiation is calculated by taking whatever the Roentgen value is and multiplying it by something called the quality factor. And the quality factor is dependent upon the type of radiation you're exposed to. If you get exposed to gamma radiation, that's the symbol for gamma, or beta radiation, you just multiply by 1 so the number stays the same. If you get hit with neutrons, whatever your Roentgen number is, you have to multiply it by 10 to figure out what your REM value is. And then if you get exposed to alpha particles, you have to multiply that by 20. So which one of these types of radiation is the most dangerous to be exposed to? Anybody? Come on, it's easy. The alpha particles? Whatever the radiation value I get hit by, I multiply by 20. It's 20 times worse than the beta or the gamma, and it's twice as bad as the neutron exposure. Okay? So this REM value is the value that the only unit that we use on our aircraft carrier when checking to see how much radiation we got. The last unit we'll talk about is a Curie, and this one's important because this is one named after Madame Curie, and it's an important unit because it's the amount of disintegrations per second for a gram of radium. And the reason this is an important number is because she's the one that purified samples of radioactive materials to get radium. This is pretty much what killed her later on in life. She gave the United States a gram of radium when it was there were only 2 grams of radium in the entire planet. She did that because they helped, U.S. Congress actually helped pay for some of her research. And that 1 gram of radium was super useful to the scientists in the United States because they used it to study all kinds of different things. So although it's not used a lot, a Curie is an important value because it gives an observable fact, which is a gram of radium will give 37 billion decays per second. And that seems like a really big number, right? But in a gram of radium, how many actual atoms are there? Are we talking about millions, billions, trillions? Remember this number? We're talking really big. So if I lost 37 billion atoms off of this number, what does this number become? All right, so minus 3.7 times 10 to the 10th. What happens to this number? Nothing. We okay with that? It's too far this way. It's not even a significant amount. I can't even do the subtraction on it and have the number change. What else? I was going to say something else with this, but I can't remember what it was. Yeah, we'll come back to it. Okay, so let's talk about this table. This is the last thing we'll talk about today. All right, so this is acute dose response effects in humans. So what's this word mean?
Big, but in a short period of time.
The size doesn't have anything to do with it. It's all at the same time.
Right.
We're okay with that? So this is, I get hit with all this. Remember that assignment that you did weeks ago when you were supposed to do it last week? What was that chart that you were looking at, that you filled out?
It was for like the radiation that you've been exposed to in millirems, right?
In millirems, yep. But it was cumulative.
But it was over a year.
It was cumulative over a year. So you guys were somewhere in the 300s, 350s, somewhere around there. And here we are. The lowest number we're going to talk about here is 1,000. So you're being exposed to 300 per year-ish. And we're saying, okay, so let's say you're exposed to 1,000 all at the same time. What happens to you?
It says no measurable effects.
Nothing. Except,
The possibility of a tumor.
well, you need to be more specific about that.
It says a statistical increase of tumor incidence before age of 10. Oh, so it's not in adults.
So you're missing, that's true, but you're missing one more thing.
In utero.
What does that
In
mean?
infants. when they're not born yet, when they're in the uterus.
Okay, so if a pregnant woman is exposed to 1,000 millirem all at the same time, there's a statistical increase that the child will have a tumor before the age of 10.
Yeah, you didn't notice that?
Why? Why the child and not the mother?
They're more susceptible to it.
Why?
They're
Because
undergoing
you're-
more cell
you're-
division.
All of their
Yeah.
cells are undergoing cell division, right? The only time that radiation could cause you problems is during cell division, during mitosis. So if mitosis is happening, then there's a better chance that this can cause problems for you. And if you're in utero, all of your cells are undergoing mitosis. So that means all of your cells have the potential to be affected. So this fact right here is a reason why a bunch of retired nuclear power workers during the tsunami, Fukushima, am I saying that right? When that nuclear power plant got hit by the tidal wave and broke apart and radiation went all over the place, about 2 weeks after the incident, a bunch of like 70-plus-year-old retired nuclear power plant workers said, hey, we'll go in and do cleanup work and we'll go in and do testing work. You do not send those 30-year-old guys in there. We'll take care of it. So I know it sounds a little like chivalrous, but does it scientifically make sense?
Yeah, because they're not really undergoing as much cell division.
They're a teeny tiny bit cell division. After like there were like 80-year-old guys that were going in there with meters, checking dosimetry meters, checking for radiation hotspots. Okay, I mean that he was pretty much okay because all of his cells were not undergoing mitosis. So it was great. And there were dozens and dozens of guys that went in and actually took the place of these 30, 40-year-old workers, 20-year-old workers that had families or wanted to have families and weren't exposed to the high levels of radiation that these guys were, and basically nothing happened to them. Okay, so what happens if I increase this by a factor of 10? So I go from 1,000 up to 10,000. Again, there's no effects. You're not seeing any of this stuff. But again, if this happened as an embryo, there's going to be an increased chance of having abnormalities. So far, what have we learned about exposure?
It's hard to get actual ill effects from exposure unless it's in like really extreme amounts.
No?
Oh, it affects younger people?
Keep going with that. It affects unborn babies more than anything else. So these first two are like, hey, do not have a pregnant woman anywhere near this because it will affect that baby that's in utero. Like, no effects for the first two unless we're talking about someone who's in utero. Okay, so again, now we're at 10 times more than that, so 100 times more than 1,000, and we're again having no overt effects. Meaning, if you got hit with, if we do the math on that, that's a 100 rem, not millirem, but 100 rem, and you wouldn't be able to tell that you got hit with that 100 rem. We could do a test on you to check your white blood cell count, and it would drop, and you actually will probably lose some time in your life, but it's going to be at the end of your lifespan, shortening is X number of days based off of the amount of radiation that you got hit by. So you might lose 6 months of your life by being hit by it, but when you got hit by it, you didn't even notice it. But if I jump up to the next step, so it's sort of the way earthquakes work, right? 3, you probably can't even feel it. 4, yeah, you might feel it. Nothing's really happening. 5, there might be some shaking. 6 is knocking buildings down. So I go from not being that big a deal to catastrophic destruction. And that's what happens when I hit 1,000,000 millirem. You immediately know you got hit by it. You're nauseous, you're vomiting, you're dead within a day to 2 weeks. And the reason you die is twofold. You can't make red blood cells anymore because your bone marrow is dead, and you've blistered your small intestines. So what's wrong with that?
You can't absorb nutrients.
You can't
or-
absorb nutrients, period. So in the same way, if you have a scar on your arm, like you've changed the condition of that membrane. Same situation here. You basically just starve to death. Is really what it works out to be over those 2 weeks. And then the last one is really what people think about when they think about radiation. It's this 10,000 rem or 10 million millirem. Blink, you immediately prostate, like bam, I get hit with it, and I just go down to the ground, and I'm dead within a couple of hours, at most a couple of days. And really what's happening is your entire central nervous system has been compromised, and all of those nervous cells are dead. And so it doesn't take very long. How could we possibly know all of this?
Had to happen to somebody.
Who
Had
did
to
it,
happen.
who did it happen to?
People in the third. Oh.
Japan. Kalena's right.
Yeah,
So Hiroshima and Nagasaki, these people who were around the blast radius, they were asked questions like, where were you when this happened? And so they knew how far away they were. They could test if you were standing next to this building, they could go test that building to see how much radiation it got exposed to, and then apply that radiation to you, and then figure out how much radiation you were exposed to acutely. And then from that point forward, they could say, okay, you were pregnant, you weren't pregnant, and they could check to see even later on in life, like what's going to happen to you. So all of this is actual statistical data that we drew from Hiroshima and Nagasaki. It's not like we had to actually test people. We just, it was an unplanned test. Not unplanned so much as they weren't planning to do a test, but it happened. Might as well learn something out of it. Is really what it came out to be. Okay. So next time when we come back, we'll talk about inverse square law of radiation, and we'll talk about shielding and how shielding can be implemented to protect people from being exposed to ionizing radiation. Anybody have any questions?
By shielding, do you mean like with lead or?
There could be. Some things are shielded by lead very well, and some things lead doesn't shield at all for. So it depends on the situation. Anything else? Anybody? I applied the algorithm to all of your exam grades, so you can go look at that. Exam grade 1.
Thank you.
Pretty much everybody's went up. Some of yours went down.
Really?
No.
Okay.
Okay.
That's what I used to be afraid of whenever curving when I was younger. I thought getting higher grades would make your grade go lower after the curve.
Well, if the class is truly curved, then it's somebody's got to get an A and somebody's got to get an F.
Yeah.
That's just how that works. I mean, it would be sad if you got a 98 on an exam and got an F, because everybody else got 100s and 99s. The guy that gets a 99 gets a C, and the chick that gets 100 gets an A. The guy that gets a 98 gets an F. So don't ask for your stuff to be curved. Curve's bad.
Curve bad.
Stats are not forgiving. Okay, if that's nobody has anything else, then I'll see you guys on Thursday.